Strategy 2, Chemoselctivity. 1. The relative reactivity of two different functional groups, such as NH2 and O. 2. The reaction of one of two identical groups, we might want to make the monoether. 5. 3. The reaction of a group once when it might react twice as in thiol synthesis. Guideline 1. If two groups have unequal reactivity, the more reactive can be made to REAC alone. Compare the basicities of ammonia and water, so reaction with acetic anhydride gives the amide we want without any of the ester. 3. The synthesis is straightforward. Nitration of phenol needs only dilute nitric acid and the reduction is best carried out catalytically. The synthesis of cyclohexane. Selectivity between two oxygen nucleophiles might sound more difficult, but when one is an alcohol and the other a carboxylic acid, there is no problem. The local anesthetic cyclohexane 12 is obviously made from the carboxylic acid 13 and amino alcohol. The acid 13 is our concern. We disconnect the ether linkage 13A on the alkyl side so that the SN2 reaction works. Chemoselctivity now arises as 15 has O and CO2H functional groups, which will act as a nucleophile. The answer is that it depends on the pH. 515 is a neutral compound. The O group is more nucleophilic than the delocalized CO2H group but is not nucleophilic enough to react with an alkyl halide. We can increase its reactivity by adding base and, between about pHs 5 and 10, it exists as the carboxylate anion 16. We don't want this as it will react at CO2 rather than at O, but pHs above about 10 it exits as the dianion 17 and now at last arrow is more nucleophilic than CO2. All we need to do is to use two equivalents of a strong enough base with suitable alkyl halide and we shall make our ether. As 14 is rather unreactive secondary alkyl halide, we need a good leaving group such as iodide. Guideline 2. If one functional group can react twice, the product of the first reaction will compete with the reagent. The reaction will stop cleanly after one reaction only if starting material is more reactive than the product, so the reaction of an alkyl halide with NaOH or Na2S cannot usually be made to stop after one alkylation as the anion of the first product is obvious in reaction with Na2S. Less obviously with NaOH. The first reaction 18 gives the thiol 19 but this is in equilibrium with Rs and a second displacement 2. 0 gives the sulfide 21. We shall see shortly how to get round this problem. A more important example, the failure of the alkylation of ammonia to give a useful amine synthesis has chapter 8 to itself. Reactions of this sort are successful. The synthesis of chloroformates from alcohols and phosgene, or a phosgene equivalent, is a useful example. We shall need benzyl chloroformates 21 in the next section to introduce an important protecting group. As it is an ester, disconnection to benzyl alcohol 22 and phosgene 23 look good, but the product 21 is itself also an acid chloride and looks as thought it might react again to form dibenzyl carbonate, but in this case there is delocalization 24 in the product that is not present in phosgene and the carbonyl group of 21 is much less electrophilic than that of phosgene. The synthesis is successful. The halogenations of ketones in acid solution, chapter 7, is another example where a reaction occurs only once. Guideline 3. Problem from Guidelines 1 and the second of may be solved by protection groups. If we want to react the less reactive of two functional groups, we protect the more reactive. If we want a reagent to react once when it could react twice, we protect the reagent. It must be easy to add and easy to remove as we are adding two steps to our synthesis. In an ideal world, no protecting groups would be needed, but just look at any recently published synthesis of any moderate complex molecule and you will see several protecting groups. protecting groups have chapter 9 to themselves. A classic case is amino acid chemistry. The amine is more nucleophilic than the carboxyl groups, so, if we want to use the carboxyl nucleophilic, we must protect the amino group. Benzyl chloroformate 22 is often used in this way. It cleanly acylates the amino group to give the carbamate 26, whose nitrogen atom is much less nucleophilic because of further conjugation 27. If you compare 23, 22, and 26, you will see the carbonyl group becoming less and less electrophilic. The anion of 26 will now react at oxygen, CO2 in basic solution, with electrophiles. The synthesis of thiols 19 is well managed if thiourea 28 is used instead of NASH or NA2S as the nucleophile. Thiourea is itself highly delocalized, but it is still a good nucleophile for saturated carbon through the sulfur ATO 29. The product is a theronium salt 30 and is not nucleophilic at all, being a cation. Hydrolysis with aqueous base liberates urea 31 and the thiol 19. The sedative and tranquilizer captadiamine 32 contains 2 sulfides and 4 CS bonds. Disconnection next to the more central sulfur atom 32 could be of either CS bond. The one chosen leads to an available, but unpleasant, amine 34 and thiol 33. Thiol 33 was made by the thiourea method from 35, and further disconnection by the methods from previous chapters takes us back to available benzene thiol 39. The first sulfide needs only a weak base as benzene thiol is acid and the electron-donating bus group directs para. The rest is straightforward. Guideline 4. One of two identical groups may give a reasonable yield by a number of methods. A. In the same way aquadeline 2, if the product from the first reaction is less reactive than the starting material, double reaction may be avoided. Partial reduction of meta-dinitrobenzene is an example. Nitration of nitrobenzene 40 is difficult but succeeds with fuming nitric acid, about 90% HNO3, in sulfuric acid, and gives only the meta product 41 is expected from the deactivating nitro group. Reduction with NaHS cleanly gives M-nitroaniline by reduction of just one nitro group. The reason is that reduction is electron donation and the very electron withdrawing nitro group encourages this. So the product 42 is less easily reduced than the starting material 41. B. If the starting material and the mono-reacted product are of roughly equal reactivity, reaction with one equivalent of reagent may give a moderate yield by the statistical method. Treatment of the symmetrical diol 43 with strong base gives a mixture of monoanion 44, starting material 43 and the dianion. If the mixture were perfectly statistical, and each species equally nucleophilic, we should expect 50% 44 and 25% each of 43 and the dianion. It turns out that the starting material does not react with ETBR and there is evidently less of the dianion, presumably because the two anions are near enough to destabilize each other. The yield of the monoether 45, used in a synthesis of vitamin E, is 65%, substantially higher than 50%. C. The best method is to combine the two identical functional groups into one functional group that reacts once to give a product of much lower reactivity than the starting material. This cannot always be arranged, but silic anhydrides such as 48 are very useful reagents. If either 47 or 48 are combined with methanol in acid solution, the diester 46 is formed, but in basic solution the anion of the monester 49 is the product and the remaining acid group can be transformed into, say, the acid chloride 50 so that each carboxylic acid has been activated in a different way. The method works because methoxide attacks either carbonyl group 51 displacing the carboxylate anion. The product under the reaction conditions is 52 and methoxide will not attack another anion to make the diester. Neutralization gives the half ester 49.